The number of brown squirrels X in an area of woodland can be modeled by the following differential equation. Question A. Find the equilibrium population of brown squirrels suggested by this model. To find the equilibrium population, we should consider derivative with respect to time to be equal to 0. Why? Because derivative with respect to time, it's a rate of change, and at equilibrium rate of change is equal to 0. So it to be equal to 0, we can see that it's a product, and the product to be equal to 0. Possible solutions are x is 0, but it's impossible because it is given that x is greater than 0, and another solution arises from this to be equal to 0, and it's clear that it's just x is 2000. The next is explain why the population of squirrels is increasing for the values of x less than this value. So for x less than 2000, and we remember that function is increasing when derivative is greater than 0, and the function is decreasing when derivative is less than 0. So we should just consider derivative and show that it's positive for these values of x. So dx over dt is positive. It's clear because it's positive, it's also positive, and hence product is also positive. Hence x of t is increasing. The next, let y be the number of black squirrels in the woodland, and it is given that the populations can be modeled by the next differential equations. T is measured in tens of years. An equilibrium point for the populations occurs when both dx over dt is 0 and dy over dt is 0. Question B. Verify that x is 800 and y is 600 is an equilibrium point. So we need just consider dx over dt and dy over dt for these values, and just when it shows that it's 0 and it's also 0. So just substituting, we get and it's clear that it's 0, and dy over dt hence this point is an equilibrium point. The next, find the other three equilibrium points. So we should consider it to be 0, it's also to be 0, and it's clear that, that when x is 0 and y is 0, we get a solution. So it's the required point 0 and 0. Oh, let's write x is 0, y is 0, and again you can see that it's a product, and it's also a product, and product to be 0, and here a product to be 0. The possibilities are this is 0 and this is 0, and this is 0 and this also is 0, and if you solve this and this as simultaneous equations, you get this solution, which is already known. And what are other possibilities? It's when this factor x is 0 and this factor is 0. Provided x is 0, you can see that y is 3000. So when x is 0, y is 3000. And when this factor is 0 and this factor is 0. So when y is 0, you can see x is 2000. The next. When the two populations are small, the model can be reduced to the linear system. Question C. By using separation of variables, shows that the general solution of this is x is a times e to the power of 2t. So it becomes dx over x is 2 times dt. Then integral, and dx or 1 over x dx, it's what? It's just ln. In general, it's of the absolute value, but here it is given that x, y are positive. So we can write directly ln of x is 2t plus some constant of integration. Then how to undo this ln? By definition, definition of log, or for example, log 2 8 is 3y, because 2 cubed is 8, and ln is just log to the base e. Hence it becomes x is e to the power of 2t plus constant, and it's just like 2 to the power of 3 plus 5, it's what? 2 cubed times 2 to the power of 5, and it can be rewritten as e to the power of 2t multiplied by e to the power of c, and it's a constant to the power which is also constant, so constant to the power constant is just another constant, and it can be rewritten as another constant times e to the power of 2t as required. And notice that in general, if you don't know whether x is positive or negative, and if you keep absolute value of x, you get like this. But you remember that if x is positive, you can just write x is, because absolute value is just x when x is positive, but when x is negative, it becomes, or minus arises, it becomes negative some constant, but negative constant is just another constant. But anyway, it's a constant to be found, and in general, you may rewrite without absolute value just x. Why? Because this constant will take into account whether x is positive or negative. And the next. Write down the general solution of dy over dt is 3y. So it's absolutely the same. So y is what? Some another constant times e to the power 3t. The next. If both populations contain 10 squirrels at t is 0, so when t is 0, x is 10 and y is 10, so we can find what? A and b. Use the solutions to parts C to estimate the number of black and brown squirrels when t is 0.2. So to find the x or at 0.2, we should find constants firstly. So just consider when t is 0, so x of 0 is just a, and it is given that it's 10, so a is found, and y at 0 it's just b, and it's 10. Just b because e to the power of 0 is 1. And then x of t becomes 10 e to the power of 2t, and y 10 e to 3t, and hence we can find at any point, and we need at 0.2, so 10 e to the power of 0.4, and we need give your answers to the nearest whole numbers, and it's just using a calculator. It's 15, and y at 0.2 it's 10 e to the power 0.6, so it's 18. The next. For larger populations, it is used Euler's method to find the long-term outcomes for the populations. A step length is 2 years, t is 0.2. Write down the expressions for x n plus 1 and y n plus 1. Just using the Euler's formula, It is given in a data booklet, and it says that the next value of a function is the current value xn plus step here 0.2 times derivative at the current point, and derivative is dx over dt. We just use this and just rewrite. And for y, the next, given that the initial populations are find the populations of each species of squirrels when t is 1. So just using a calculator, first of all, choose mode, and it must be sequence mode here. Then we enter these formulas, but for the calculator n-1 it's like n current point, n plus 1 it's n the next point, and let u be x, v be y, and w be time. Here actually time is not involved directly, and it's not necessary to set w, but it may be useful to avoid mistakes. So these formulas become, for x it's u of n-1, and notice that you should always write of n-1. So it's xn, so u of n-1 plus 0.2 over 1000 times x, so u of n-1 times 2000 minus x, which is u of n-1 minus 2 times y, which is v of n-1. And the next is the initial value, it's 100. The next, y, v of n-1 plus 0.2 over 1000 times v of n-1 times 3000 minus 3x, which is 3 times u of n-1 minus y, which is v of n-1, and the initial value it's 100. Double its time, step is 0.2, so it's w of n-1 plus 0.2, and the initial value is 0. Then we can use this, and we can choose pairs, y with x, and in general you can see it's y with time, and it's x with time, and we can use table, and it is chosen x and y, and it's just easy to deduce that the first point it's when t is 0, so it's 0.2, 4, 6, 8 and 1. Or to avoid mistakes, you may just choose x with time, and from a table you can see clearly that w its time it's t is 1, and this value 4x, and absolutely similarly if we choose y with time and then table, and you can see that when t is 1, y is this value. So at t is 1, x is this value, and y is this value. The next, use further iterations of Euler's method to find the long-term population for each species of squirrels from these initial values. So you may use table, but it's more useful to use just graph. But for graph we need window, and n is number of points, but I know what limits should be just from the next question. You should set x. X is from 0 up to some value to y, for y from 0 to some value, and in general notice that you may choose again x with y, y with time, x with time, and with time it's not required here, but in general it may be required for some problems. But here we need x, y with x, so we choose this, and graph you can see directly, and if we trace from this starting point, you can see that it tends to what? To one of equilibrium points towards 0 and 3000. Or from a table x, y, you can see that x decreases, y tends to 3000. So number of brown x goes to 0, and number of black y goes to 3000. The next use the same method to find the long-term populations of squirrels when the initial populations are 400 and 100. So when x is 400 and y is 100. And in general, for window you just choose some values for x, for y, maximum values, a graph to be seen. And when, so we need just change the initial values. It's 400 for x, 100 for y, and the same. Oh yes, you may just consider a table, but using just a graph you can see that it looks like this, and you may deduce that it tends to what, to this equilibrium point, which is what 2000 and 0. Then so we write that number of brown x goes to 2000, number of black y goes to 0. The next, use Euler's method with step length 0.2 to sketch on the same axis the approximate trajectories for the populations with the following initial populations. And the same, but we need just just change the initial value. So for x is 1000, y is and again just graph, and you can see it looks like this, and you may deduce that it tends again toward 0 and 3000, and or just using table you can see that y decreases then increases, x decreases. So it looks like this. Then for x is 1500 and y is 1000, you can see it looks like this. Or from a table you can see that x decreases then increases, y decreases, and when you draw it, so 1 2 x 1 2 3 y, and x the first point 1000 is this one, and y is 1500, and it looks like this and tends to 0 3000, and this the second is here and looks like this, tends to 2000, and f given that the equilibrium point at 800 600 is a saddle point, scale the phase portrait for x is greater or equal than 0 and y is equal there is greater or equal than 0 on the same axis used in part E. And let's consider, or if we consider, it's not necessary but it's interesting if we consider equilibrium point 800 and 600. You can see it looks like it's just a point, and when you just add the previous two curves for 100 100 and 400 and 100, and it was what, something like this and something like this, and we should add arrows. It's definitely it tends to this, so in this direction, in this direction, and in this direction. And that's all for this question.